Well, good afternoon. My name is John Dyke. I'm the CEO of CESMII, and it's an honor and a privilege for me today to introduce Aaron Purcell to deliver a keynote for our annual member event. Obviously, this event was to take place back in March, and Aaron and team had prepared to fly to LA and deliver this in person, face-to-face, but Aaron, obviously that didn't happen, but I'm thrilled that I can introduce you virtually today to our membership and the broader ecosystem here, and ask you to share your perspective on smart manufacturing and ExxonMobil's perspective in this space. It's an honor to work with an organization like yours in that there's significant alignment between what ExxonMobil is looking to do as you drive and invest in your ecosystem, and obviously ours from a broader perspective in this smart manufacturing space, right? The necessary investment in open systems and interoperability and security and sustainable systems. I think those are core values among many others that that we share, and about which I think you'll be sharing today. So again, thank you for your time. Thank you for your organization's support of CESMII. On a brief logistics note, I'd like to ask those in attendance today, if you have questions, please use the Q&A section in our system here, in our Zoom system, versus the chat system. We'll try to monitor that, because every now and then a few questions get posed in that environment as well, but we would ask that you would pose any questions for a live Q&A after the fact, after the presentation, in the Q&A window. So with that, Aaron, thank you again, and I'll look forward to your conversation.
All right, John, thank you for the introduction, and also for the invitation to come speak today. So there are other ExxonMobil folks who have been involved with CESMII for some time, but this year was my first opportunity to get to know a little about your organization and your mission, and I'm glad to be able to be here to share with you some things about ExxonMobil's view of computing and data needs for automation. As you say, I was hoping to meet you guys in person this year, but circumstances being what they are, we'll just have to settle for being thankful that technology gives us some options like this one. So a little about myself before we start, just so you know where I'm coming from. I joined Exxon Chemical in Baton Rouge, Louisiana in 1996, and over the next 23 and a half years, I've had roles in a variety of process control applications positions in the US and overseas. So what I want you to understand is I'm with ExxonMobil, but I'm not the upstream production part. I don't pull the oil out of the ground, right? The majority of my experience is petrochemical manufacturing automation at sites, and now from the central engineering office in Houston. So refining and chemical plants are in my background. So manufacturing automation is what most of my career has been about. The second thing that I want you to understand about me is that back in January, I went car shopping. And it was the first time I'd been car shopping for some time. I tend to drive a car until it's just not feasible to do that anymore. But this time, the last car I bought was in 2013. But it was time to pass that vehicle on to my son for college. And so I did that, and I went out car shopping. And what I saw pretty quickly is that the cars available in January of 2020 were very different from the ones that were available in 2013. I'm not a high-end guy when it comes to car shopping. Utilitarian is maybe the word that comes to mind. But even in the lower end area of the vehicle market, there were new sensors on these cars, a camera in back and radar in front, some things that had been available only on higher end vehicles several years ago. And so it struck me the difference in just a period of 7 years of how much the market had changed, how much the product that was available to the end user, the consumer like me, how much that product was different, how technology had made a change in that area. When I bought my last car 7 years ago, I was stuck with its technology package, which it was fine at the time. But you know, over the years, I saw commercials for new things coming along. I rented some cars along the way that had some of those features that I didn't. And I thought to myself more than once, man, I wish I could have that. But you know, migrating to a new system here was not economical. It just didn't make sense to go buy a whole new car for those things. What if I had to keep that car for 40 years? What if I were still driving the same vehicle that the first one that I bought was in 1986? What if I were still driving that vehicle around? I tell you what, I would have some serious car envy for anybody else who was on the road, who was not in one of those things. An Oldsmobile Forenza, by the way, which probably none of you have ever heard of, and there's probably a good reason for that. But driving a 40-year-old car, that's kind of where some of our control systems are right now. Some of our control systems were installed in the late 70s and the 1980s, and they're getting to the point where they're just going to have to go. We're going to have to put something else in their place in the near future. And so as we look at a pretty sizable piece of work to replace DCS technology that was installed back in the 1980s, we have the same situation that I had with my car. I want to take advantage of modern capabilities, the industrial Internet of Things, cloud computing, machine learning, data science, all those cool words. A lot of things that were not present the last time that we went DCS shopping. But current tools are not the end, right? We also want systems that will allow us to incorporate new capabilities as they appear in the future, so that we don't have to go buy a whole new car to get some of those. And so as we talk about objectives for improved architecture and some of the aspirations that we have for the CESMII innovation platform, that's kind of the analogy that I have in my head. It's about driving my car and what would I do if I had to do the same thing for the next 40 years. Let's see if I can figure out how to advance the slide here. There we go. All right, so what we're going to do today, I'm going to kick off by revisiting a couple of concepts from the 2019 CESMII meeting and pull in a couple of slides from there. And then I want to discuss two different initiatives within ExxonMobil to develop a process control infrastructure that is suitable for those challenges. And then I'll conclude at the end with some remarks about how our expectations mesh with the CESMII objectives. So, motivation and reconnect. So let's start by revisiting a couple of slides from last year's CESMII presentations. This slide was presented by Haresh Malkani last year as part of the 2019 CESMII project portfolio. And Haresh showed this slide to introduce the concept of a platform. What is a platform? What does it mean when we use that word? So a platform is an environment to let consumers who have problems and who have specific data, allow those consumers to interact easily with technology providers who have tools and solutions to address those problems and that data. And so there are a lot of common examples in the consumer market, and the most ubiquitous one maybe is the smartphone. It's a common environment with standards so that a lot of suppliers can develop apps for users, and you can go pick the apps that fit your problem and your information to do the things that you want to do with your device. And my instantiation of my iPhone might be very different from yours. There is a lot of activity by big players in the market to provide the same sort of platform for manufacturing. They want to bring together users who have manufacturing problems and data with suppliers who have technology for analysis and insights. And so trying to do the same sort of thing for manufacturing systems that we are doing for consumers with the smartphone is part of what we're doing with platform development here. So the second slide that I want to show is from John's keynote speech last year on the CESMII vision. So there's a picture here of the legacy Purdue model. And I have to tell you, you could plop this picture down in front of any process control engineer in any one of our sites, and they would look at it and say, oh yeah, that's exactly what we do. Is this an ExxonMobil slide? That's what they would say, because this is exactly what we have. The Purdue model has a very hierarchical structure. You've got data flowing from one layer to the next, and most of the computing capability, maybe all of the computing capability, may be on site. So if you look at these levels of that hierarchy, there are a whole lot of different functions and vendors that get crammed into level 3. So at least for us, levels 0, 1, and 2 are proprietary platforms. There's a limit what we can do on those platforms. We get to level 3, we've got a little more flexibility there. And so we have a lot of different functions that we try and cram in there in level 3 because that's where they'll run. And so that data pipeline there can get choked as we feed a lot of stuff up from the process, which is where all the useful data comes from. We feed that data up into the different functions at level 3 and to some degree at level 4 as well. And there's just a lot of data passing back and forth through, for example, through level 1, level 2, where we might not be using it at all. If you compare that to the smart manufacturing model from John's slide, the architecture difference here is you see different functions that are connected independently to a central data hub. And so you've got some of those capabilities even moved up into the cloud and off-site. John and Haresh both made the point last year that we can't afford to support lots of different methods of data management and interface for every vendor's technology. So one of the central ideas here is about standardizing the acquisition and availability of data in that central hub. So anyhow, if you heard last year's presentations, this is information that you've all seen before. I picked these slides just because as I start to talk about ExxonMobil's internal work on automation solutions, I hope you can recognize that some of the features that we're working on are similar to ideas that you see here. All right, digital transformation, the big buzzword. Everybody wants to talk about being digitally transformed. So manufacturing does too. We talk about it here as well. We toss that term around a lot and different people may mean different things by it. But what does digital transformation look like for manufacturing? So what I have here are some thoughts about what it means for us. First of all, improvements to OT and IT platforms are required to enable the use of modern data science methods and implement new future capabilities. So it's obvious that we need some improvements to our platform, both to use current technology and to enable access to future solutions. Again, this is all about not being stuck in the same car for the next 40 years. The words that we use to describe our requirements around our next generation system are these 5: openness, interoperability, software portability, security, and data ownership. The first 3 terms up here we're going to talk about over the next few slides. So I won't say much more about them here. Security is not a focus of today's talk, but it is clear that greater levels of remote connectivity, as we start to incorporate cloud computing and higher degrees of connection to the internet and all that those kinds of connections will require new approaches to security. Data ownership, I won't spend a lot of time talking about that either, although the subject will come up, but what we mean by that is it's important to us that we own the data that we generate. Our platform needs to allow technology providers to access that data to help us with analysis and other things like that, but the data has to live with us. We generate it, we own it, we want to give other people access to it to help us with some of that problem analysis, but the data is ours and it has to live on our system. And then finally, a suitable platform enables collaboration between manufacturers, suppliers, and universities where some of this technology is being developed so that we can develop and deploy innovative techniques, including an environment for prototyping and development. So what does all that mean? On the subject of collaboration, we know that solutions in the future are not always going to be prepackaged and off the shelf. And so we need a way to develop and apply new solutions rapidly by working with innovators who have ideas. They need to have access to our data. We need to be able to prototype and deploy things that we get from them. So that's what we need. That's what we say we need anyhow. What are we doing about bringing some of these capabilities? So I have 2 initiatives to talk to you about today that address different parts of this need. And so the first initiative is the somewhat more public one, which is the Open Process Automation Initiative. Officially referred to as the Open Process Automation Forum of the Open Group, because if you say open twice, people know that you really, really mean it, right? So the forum started in November of 2016, and its purpose, its mission, is to define industry standards that we believe are suitable for an open, secure, interoperable process automation architecture. So developing standards around which we can build one of these systems like we say we need. The forum has 96 member organizations. Last time I looked, it could be higher now, who knows. But of those member organizations, 22 of them are operating companies. We had 6 of the 7 global DCS vendors are there, hardware, software, systems integrators. We're trying to get participants from kind of every different piece in the big picture so that we can all work together on an integrated solution here. What has the forum accomplished in the 3.5 years that it's been around? So I said the mission was about defining industry standards. The forum has published versions of those standards. They're at work on version 3. I'm not going to talk much about the documents here, except to say that the standards are developing, and the evidence that those standards are viable is the second bullet point here, that there is a working system prototype that has been developed within the forum, and we'll talk some more about that in a couple of slides. But the point is, people are building things to the standards, and they work. If you're interested in a little more information about the forum or any of those documents that are listed there, they're available at the Open Group site at opengroup.org, and you can peruse them at your leisure. All right, so what we have here is a reference architecture picture for the OPA system. If you remember from a couple of slides back, that picture of the Purdue hierarchy where we've got level 0 through level 4, that hierarchy has proprietary hardware, proprietary interfaces and networks, vendor-controlled software access. It has security that's sort of bolted on around the outside. And by contrast, what we're aiming for with OPA here is interfaces and networks that are based on open industry standards with interoperable hardware that allows multiple vendors to supply components. We have open software access and security that is designed in, although as I say, we're not talking very much about security today. I want you to notice the similarities between this picture and John's earlier slide from last year. The levels of the hierarchy have largely disappeared here. There are lots of functions that are connected to a central bus rather than a top to bottom data flow, although I'll point out one maybe significant difference, at least in the instance that we're looking at here. That bus is local and not up in the cloud. So this bus for us is on site. We have the capability here for connection to above site computing resources. So up in the upper right here, the external data center connection. And there's a standard open platform to make sure that we don't need a proprietary technology stack for every function that we have here. So note the color scheme on the slide here. So you've got some blue things and some yellow things. The yellow components here are things that are new, things that are being developed specifically for OPA. And the new items are the distributed control nodes. So down in the lower left, you'll see some DCNs down there and a description below of what happens. Those are kind of the edge computing devices that do a lot of the computing that we associate with level 1 to level 3 functions in our hierarchy today. That real-time service bus that runs across the middle of the slide there, that's new. And at the top, the yellow box for the advanced computing platform with some computing capabilities that we'll talk about in a few minutes. We do have blue boxes on here for existing legacy technology for the things that are in our plants. Largely, those would remain untouched until we just have to replace them because our approach to these things is much the same as my approach to cars. You just drive it until you can't anymore. But all of those systems would need a new interface to the OPA system. So you see little yellow boxes there representing a new interface connecting each of these things to that bus. All right, this is a development timeline for the OPA system. Now, I acknowledge that this is kind of a busy slide, so we're not going to talk about everything on it, but there are 4 things that I want you to see about this slide. The first thing is that I said at the beginning that the forum was charged with developing standards. And so down at the bottom, you can see some yellow diamonds and some green diamonds that are associated with milestones for the software standards, which are being developed by the OPA forum. And the hardware standards, the green diamonds are for the hardware standards that are being developed in conjunction with the Georgia Tech Research Institute. And so you have development milestones for those standards, and over on the far right-hand side at the bottom, you see a red diamond for integrated software and hardware standards. So those 2 lines of development converge here on that red diamond that is currently located in 2023. The second thing that I want you to notice about the timeline here is kind of in the upper middle, the orange and blue boxes that say prototype and test bed. The orange box here is the timeline for the working prototype that I told you before existed. And again, we'll talk a little more about it on a future slide, but that prototype was developed with Lockheed Martin and Wood. And it originally ran against a simulation environment, but nowadays it is connected to a real hydrocarbon process with physical I/O. So real live operators are sitting at a console running a small unit at very low rates with a system that used to be a DCS, but now it is OPA. The blue box here, that's the test bed. So there is a second facility, a test bed being developed in the Houston area, where our collaboration partners are going to develop and deploy test bed experiments to prove the capability of the system. So prototype and test bed is putting those standards into practice with real physical hardware to run real systems. The third thing that I want to point out about this slide is that I mentioned collaboration partners when I was talking about the test bed. And you can see across the bottom the logos of the collaboration partners that I have in mind there. So all of these are operating companies, and they have agreed that they will install gear on the test bed, they will conduct experiments on the test bed, and then they will proceed to field trials. Those are some of the green boxes up above, industry field trials. They will proceed to field trials in their facilities if all goes well with the test bed. And these participants, these collaboration partners, have agreed that non-proprietary results will be shared from this evaluation. So the forum will let you know how we're doing with these trials. The fourth thing I want to point out about the timeline here is something that is not ever explicitly stated, but it's inferred. So I want to make sure the inference is right out there in the open for everybody. When we use the words open and interoperable and portable and things like that, we're not referring just to gadgets that sit in a network. We're also talking about how we behave as a company. Sometime around 1999, I was still a relatively new process control engineer in Baton Rouge, and I was a member of the local AICAG chapter there in Baton Rouge that met on campus at LSU. And I went to one of the local chapter meetings, and the invited speaker was from a software company that does work in real-time optimization. You would recognize the name if I said it. But he came, he was talking about the kind of the history of his company, how they got involved in real-time optimization, the history of the development of the technology, not just in his company, but also things that other companies were doing. So he mentioned other operating companies and their own efforts around optimization over the years and what they were successful at and not so successful at. And in the end, he said, so he was talking about all these operating companies, and he said, and then there was Exxon. We never knew what Exxon was doing, he said, because they would never tell us. And I sort of sat back and said, well, okay, I'm not going to tell you either. But my point is that that's sort of how we behaved as a corporation for a long time, is that nobody really knew what we were doing and we didn't have any interest in telling them. And so that's just how it went. But when you look at this slide and you see a number of other partners on here, some of them vendors, some of them researchers, some of them operating companies, I want you to understand that the picture here is a more open way of interacting with the world than we have demonstrated in the past. So there is a balance to be struck to find the level of idea sharing that makes the whole space better without losing competitive advantage in areas where you think you have core competency. We're working to try and get that balance right. But my point is that this picture is a change for us. It is a different way for us to interact with other people in this space, so that hopefully 10 years from now, people won't talk about it and say, well, we never knew what Exxon was doing, because they would never tell us. So the prototype system that I talked about, what does it actually look like? So this picture is modeled a little bit on that reference architecture diagram that we looked at a couple of slides ago. But this is a picture of kind of what it looks like with actual devices stuck on it. Because the devices for OPA are built to open standards, we can have multiple vendors supplying parallel functionality, all communicating on that central bus. This time it's a blue bar going across the middle of the screen. So we have in the prototype system, if you start at the lower left down there, the DCNs, the distributed control nodes, the process connected devices where a lot of the fun happens. We have DCNs from Phoenix Contact and Intel, just as examples. We have Intelligent I/O from Yokogawa and Moxa. In that box at the top that says Advanced Computing Platform with kind of the navy blue line around it, there's parallel controller functionality in here from a series of vendors. But the point of that big blue box up there is to provide some higher powered computing capability than we have down at the DCN. But the point of this slide is that vendors are already making early generations of hardware and software based on the standards that have been developed by the OPA Forum for this vision of manufacturing automation. It is being put into practice. And here's a picture of it in practice. So you see the operator screens, you see a little bit of the the unit there in the pilot plant in Clinton, New Jersey. That prototype system has been applied to that unit that was formerly DCS controlled. And as I said before, it is operating a hydrocarbon unit. You'll notice that bolded word over to the left. It says the biggest challenge is related to creating systemness. I'm not sure that's a word. If it is, it's an awkward word. But what we mean by that is look, in addition to the input and algorithm and output parts of process control, there are a number of other features that a functioning system needs to present to the users in order to make it all work. So there's security and alarming and messaging and engineering tools and integrated history collection and all those sorts of things that have to work together in addition to the basic functionality of reading inputs and calculating outputs. And so trying to create a system that worked together cohesively for the user was part of the challenge that the team had. But there it is. It is running. And the next step, as I mentioned, is test bed trials with our collaboration partners. So the OPA initiative that I just talked about focused mostly on architecture, what we're used to thinking of as kind of level 1 to level 3 in the DCS world. This second effort, autonomous operations, addresses the computing capabilities that we think we need to support the use of modern data science methods. And I'm using data science here in a really broad sense to encompass a whole bunch of different things. We won't talk about what all of them are. We call this effort autonomous operations because the word autonomous suggests that there's a higher level of decision making that we're turning over to the process control system. So how do we let machines make more of the decisions that human operators make today? So let's talk about autonomous operations. But first, let's talk about not our autonomous operations. I think everybody's aware, sticking with the car analogy for a little bit, everybody's aware that in the near future, there is a lot more automobile automation that's on the way as different companies work toward whatever it is that they call a self-driving car. And the objective there is to, again, take a lot of the decisions that human operators would normally make and let them be made by a machine. We're not working on self-driving cars, but we use this analogy to describe what we're trying to do for process plants. In general, not in every case, but in general, car makers are not inventing the base sensing technologies that you see on the slide. So the radar and the LiDAR and image processing and things like that, those are commercial technologies that are already out there. What the car companies are doing is working to integrate those functions and formulate the driving problem in a way that it can be addressed with these inputs. And formulating the driving problem, trying to say, how do I take the process that a driver goes through to drive a vehicle? How do I reduce that to an algorithm that can take these inputs and make the same decisions, or hopefully maybe slightly better decisions? What you see at the bottom here, the Society of Automotive Engineers lists some different levels of autonomy that cars might have, basically depending on what level of decision making you're willing to turn over to the machine. And we're sort of going through the same evolutionary process with process plants as well. So what do we have today? We have a lot of technologies that are on our units, on our process units today, refineries, chem plants, or wherever. So we've got procedural control, we've got optimization, we've got model predictive control, other things like that. And all those technologies are out there. They all perform their function more or less. There's not very much integration among them. And so our current state of automation is sort of at the cruise control level. It's the operator says to the plant, I want you to run at this set point, and then it does. What do we need to be better? To make the plant more autonomous so that operators make fewer decisions and machines make more of them. What do we need? Well, those are the items in the pink boxes around here. So we've talked, the box at the bottom around the modern DCS interface and better edge computing capabilities. We talked about that a little bit with the OPA initiative, but largely what we need is the ability to formulate the problem of running a plant in a way that a machine can address that problem. So we need orchestration among all the different pieces of technology that we have out there. We need machine learning and artificial intelligence to help us kind of mimic human decision making. And again, in some cases, we're looking for decision making that's better than human decision making, or at least faster and more reliable and repeatable. The effort here is to bring existing technologies into the control problem. So this is a picture of the computing structure that we're developing to support that work on autonomous operations. So this is a structure that exists in our lab. It's not operationalized at any site yet, but it's what we're working on to try and make those, try to bring those capabilities to bear on the problem of running a process plant. Now, you'll look at this picture and you'll probably notice right away that the diagram here does not look like the OPA diagram that we looked at before. So the focus here is not on the on-site DCS architecture. That's all sort of wrapped up in this purplish gray box, whatever that color is, down at the bottom that says site control system. So for the most part, the OPA system would sit in that box. The focus here in this picture is on three things. First of all, the upper layer of computing platform for data science and collaboration at level, what we used to call level 3, level 4. So the upper layer computing platform, what does that need to look like? The second thing we're looking at capabilities for offsite support. So you'll see in the upper right this connection to a vendor cloud out there. And this is still an aspirational goal. We haven't made that link just yet, but it's part of the development work. The third thing we're focused on here is a variety of new data sources. So I mentioned before with the self-driving car, taking commercial technology and figuring out how to formulate the driving problem with those inputs. And so we're working on the same sort of thing here, trying to bring commercial technology into the process control problem. So if you look kind of at the bottom center and a little to the left, you'll see representations of computer vision and image processing. You'll see a digital operator assistant here so that you can ask it a question and get a meaningful and helpful answer if you're an operator. The point here is that this system is about storage and computing that will support a new tool set. So like the CESMII platform picture that we looked at earlier, there is a significant component of this that is above site. Some of it is still within the company, but above site. So in the middle, across the middle of the screen here, you'll see kind of a blue dashed line with a distinction between site computing and above site computing. So that above site component has both ExxonMobil cloud and vendor cloud computing capabilities for functions that are non-critical. If you have a function that requires high availability, right now that's got to stay on site. It's got to keep running regardless of what your connectivity might look like that day. And so those things stay on site. But for non-critical functions, there's a lot of that can be done above site. This picture also represents ExxonMobil's desire to retain ownership of the data from our sites. We talked about that a little bit before. Vendors may have access to this through that link to the vendor cloud up there in the upper right, but only through data storage that we own. The data that's generated at our site lives in our site storage, and we can give vendors access to it, but it's still ours. The blue boxes that you see in the middle that both say modern compute platform, one for the site and another above site. That box is a collection of computing capabilities for storage and applications hosting. So what I'm trying to show you with the whole picture here is that we're working on how to incorporate more modern computing capabilities, whether it's bringing in more horsepower, bringing in capabilities that are off-site, in some cases outside our company, or whether it's using these new data sources like computer vision or the digital operator assistant or whatever. How we incorporate those computing capabilities in a way that enables innovation and collaboration. All right, we've looked at two initiatives that focus on different aspects of a process control infrastructure that we think is suitable for taking us forward into the future without us being embarrassed about driving an old car while everybody else around us has got new stuff. But these are just a couple of examples of the things that we need. What do we expect out of an entire solution? So some of the expectations that we have for a system like this are objectives that we think we share with the objectives of the CESMII Smart Manufacturing Platform. And so here on this slide are some areas where we think we have a common vision about how that future develops. So platform for rapid prototyping and collaboration with technology providers, both industrial and academic. So we recognize that innovation might be done on the fly for real life problems. And so we need to host something that facilitates work with technology providers. An open cloud computing means to provide remote support to manufacturing while maintaining security and data ownership. So we recognize that computing will not be all on site. And in fact, the methods won't all be in-house methods. There are a lot of smart people out there with a lot of useful things that we might be able to use. And we need to have a platform that lets us bring those things in from above the site and in some cases even outside the company. Industry standards for open systems to allow us to move beyond incremental extensions of current technology. So if our next step in the control system space is simply to move from a proprietary on-site system to a proprietary off-site system, then we really haven't made a lot of progress here. So a real platform needs to be open to allow easy collaboration with all those technology providers that I mentioned back in the first bullet. All right, so let's go back to almost where we started. Back on that slide for digital transformation for manufacturing, and talk about what those initiatives mean for this slide. The first bullet point here about improvements in platforms. We have a lot of infrastructure to replace in the automation space. And we need infrastructure that allows us to incorporate future capabilities. Can't be driving the same car for 40 years. Second bullet point, requirements. So those 5 terms there, openness, interoperability, software portability, security, and data ownership, those 5 terms are our description of the characteristics that we want for a digitally transformed system. The third bullet point is about collaboration. The right solution allows us to bring a variety of expertise to bear in developing solutions. So we're here, we participate here in hopes that the CESMII Smart Manufacturing Innovation Platform will exemplify these features that we want. And we want to understand whether that platform could be a component of the IIoT architecture that we want to use in the future. So I'm going to close, finally, as everyone gives a sigh of relief. I want to close with John's vision slide that we looked at in the very beginning. And the purpose of showing this picture again is to say that right now, we are that system on the left. And we want to highlight that the CESMII vision aligns in significant ways with our own understanding of how our IT and OT architecture needs to evolve to enable us to solve complex manufacturing problems. And so we look forward to the challenge of bringing that vision to pass. I want to thank you for your attention and again for the invitation to speak. I understand that we might have a few minutes at the end for Q&A. If there are questions that have been written in the Q&A box, I can't see them right now. But
I'm sorry to interrupt, Aaron. I'd be happy to facilitate a brief dialogue with the questions as they come in. So
before we do, I want to introduce Tyler Soderstrom, who I invited to participate along with me. Tyler is online here. He's one of our lead technical people who's working on both of these initiatives, both on open process automation and on autonomous operations work with the computing lab. And so Tyler's here because he's participating at more of a technical level than I am. So depending on what questions you have, he might be a better person to answer than I am. So Tyler, thanks for participating along with me today and being willing to take questions.
Glad to be here. Thank you.
Yeah, Tyler, it's an honor to have you with us as well. And Aaron, thanks for a great presentation. A couple of questions so far. One is a fairly detailed question. So between you and Tyler, I'm thinking you'll be scratching your heads. So how's that for a way to start a challenge?
What a fine start.
Yeah, exactly. So what criteria are you applying to determine where a computing workload should execute from your site, enterprise, and vendor cloud options? And maybe a subset of that is, do you envision a common interface or API between each of those levels?
So, Tyler, I'll take a little bit of a start here, and you can finish up. So, at what level should a thing run? Is how I'm interpreting the first part of the question. And so I mentioned kind of in the middle of the presentation that required availability is one of the important criteria. The higher availability that you need, generally the closer to the process a thing has to run. Now the nice thing about OPA is that given how the computing is distributed here, that it's not in the big hierarchical stack like the Purdue model, there aren't as many, I guess, levels of failure in between that can bite you. But still, if you need high availability and high speed, let's be honest, the different levels of computing capability here are going to operate at different frequencies as well. And so speed and availability have a lot to do with where we think these things are going to run. And then, of course, when you talk about vendor capabilities and things like that, there are questions of intellectual property and proprietary information and all that might govern willing we are to make some data available in some ways to external providers. But I guess the first part of my answer would be speed and availability requirements will have a lot to do with whether you're trying to put something at the DCN level, which is going to execute at high speed, or if you want to put it up higher. An obvious part of the answer is around how much horsepower do you need, right? The DCNs that I showed back on my architecture diagram, if I can go back that far. If you think about those DCNs as being roughly like your smartphone, they're small devices, they're fast, they compute, but they're not going to have an enormous amount of horsepower. Obviously, more horsepower than some of the process-connected stuff that we have today, but the really high horsepower stuff has got to go in the advanced computing platform. Tyler, any other thoughts on the decision process for where you run some of this stuff?
Yeah, just a couple of things. I mean, I think you got most of the points already, but I think one thing about the slide that shows the vendor cloud and the external service provider cloud, I think some of that would be a matter of whose technology we're using, whether it's a vendor has a solution that we can use immediately and it requires their cloud to run in, that would be something that would push us in one direction or another. If it's a piece that is intellectual property that we've developed, it would likely run in our own cloud. I think the comment about interfaces, I think that's very important too. I think that when you're talking about the Open Process Automation Initiative, really what that's all about is defining these interfaces and using standards to define them. So the agreeing on how data will flow is an important element of that. So having that openness is a key part of that. And when it comes to APIs between layers or things shown on here, common APIs would be wonderful, but I think the most important piece is that they're open and accessible.
Thanks, gentlemen. I think those are great, thoughtful responses. Appreciate that. The next two are actually much simpler before we get to a little more complex again. So
Maybe
Aaron,
we'll run out of time before that.
Well, yeah, exactly. So I'll just keep talking. But what
Go ahead.
buying in January, if you're allowed to disclose that?
What? I'm sorry, I missed the first part.
What car did you actually end up choosing back in January?
So, if you want to take a guess, what would you say if I said that the objective is if somebody sees me driving down the street, I want them to think, what a sensible person that must be. What would be the answer to that question? And the correct answer is I bought a used 2019 Toyota Camry.
I think that personifies the way you described it. I think that's
My previous car was a 2012 Ford Fusion. Also used. I only buy used cars. Don't think too much about it.
Love it. Thanks for that. So the other simple one, which I can address, is will the slides be emailed out to attendees? The short answer is the recording of the session and most of the decks of this virtual event are and will be posted on our website. We will not be emailing them, but return in a day or two after each of these sort of distributed virtual sessions, and you should find them on our website. And then back to another more meaty question. When it comes to data scientists, machine learning and artificial intelligence, to what degrees does ExxonMobil have the resources to do this today? How do you plan to grow this capability in the future? And what are the technologies you're looking for to make that possible? So that's a pretty broad question.
Yeah. So again, I'll start and pluck the easy fruit off the tree, and Tyler can let me know what I've missed at the top afterward. So do we have capabilities in-house? So like a lot of other operating companies, the subjects that you mentioned here, so data analytics and machine learning and all that are, we have not developed expertise in those areas over the last 40 years like we have in some. So my background is chemical engineering. Most of those terms didn't exist as far as I know when I was in school. But as we started to look at these initiatives, these research initiatives to work on, we did realize several years ago that to kick those things off and to get the right people to work on them, we needed to change some things about how we were recruiting. And so we have deliberately for the last few years recruited people with different backgrounds who have more data science, more machine learning, not necessarily from traditional chemical engineering process control schools, right? So we've got a few of those still around that are really good for churning out people with the traditional process control kind of background. But we have tried to expand our recruiting to incorporate people who have relatively recent academic experience in some of those areas. And I'll say that consistent with our vision of the computing infrastructure here, like is on the screen, our data analytics capabilities are fairly widely distributed within the organization. So there are lots of different functions besides process control that are trying to incorporate some of these. And so we have data analytic groups in other areas as well. We've had some discussion about interchange between those groups to swap some of our process knowledge for some of their technical expertise. But you're right to point out that it's not a traditional area for us, and so we've had to change our recruiting focus a little bit to match that. So now in typical fashion, I've talked long enough that I'm not sure I addressed the whole question. You were asking about where do those capabilities come from? What else?
Yeah, and I think you did answer head on, Aaron. So I think,
good.
I think we're good. Yeah. Yep. So,
all right, Tyler, anything to add there?
No, I think that mentioning that expertise lies in a number of groups, both from the manufacturing side or more manufacturing-oriented side, as well as the serious R&D side, the research side, and there's a lot of interplay between those groups and interaction to try and see what we can learn from each other.
that makes sense. So what technology makes up or will make up the real-time service bus? Is it Apache, Kafka, JMS, something like that?
So I think, unfortunately, we don't have a real networking expert here. I don't have a good way to a good answer for that. Exactly which technologies are being used. So I apologize for that.
No, quite understandable. In fact,
I'm not a networking guy either.
Yep, fair enough. We'll move on to the next question here. With regards to the operator interface, is there a single unified interface, or do all of these different tools and modules require their own screens and windows? And then the second part of that is, how do you make sure the system is usable by the operator?
So the big key about the operator interface is that this is where the role of the system integrator really comes into play. Because if you go back to the
Oh,
previous slide, Aaron, that shows the slide number 11, that shows
the operator interface was the right place, but
well, what you see here is a box that represents the operator and engineering consoles, and what the tool that we used to really integrate all the different data and display it in one single form was Ignition from Inductive Automation. So there was a lot of effort that was done to integrate the data from these disparate sources and display it in one coherent spot. Now, in terms of making it available and presented to an operator and having the right information there, effectively, we've been dealing with operator consoles and HMIs for a long time, and we have a lot of standards and built-up knowledge about what operators really need to run their units. So effectively, what was done was to apply the same, to basically display the same information that was there when this process was controlled by our traditional DCS, and also do some extensive testing with the operator in advance to make sure that there weren't any hidden usability problems that may be something that they really relied on that we would have forgotten about.
Got it.
So the importance, Tyler emphasized the importance of having folks on this initiative who have actually worked with operator interfaces and in manufacturing sites over the years. If you follow Dilbert, you might remember several years ago that Alice came down with a disease that was diagnosed as interface poisoning, which was just an excess of exposure to interfaces designed by engineers. And so yeah, we've tried very hard to include enough plant experience in this to create interfaces that are similar, at least analogous to things that are working in our manufacturing facilities.
Great. Well, we have 3 minutes and time for one more question. I have an answer to this question after you answer it. But the question is this: you mentioned that you may bring solutions in from outside. Many data-oriented research efforts are stymied by lack of access to adequate amounts of meaningful data. There might be clear benefits to having cutting-edge solutions innovated, working on your problems and the associated data. Are you interested in methods to make you comfortable with sharing data?
So, so I pulled up the slide here with the architecture diagram for our computing platform. And when I said that our intent was to have, to make it possible to have external interfaces in here, I said that was aspirational, that it's not something we're working on, but we haven't brought it to fruition yet. So yes, we expect that we will run into a number of problems that we need to work out around who gets access to what and how. But it is absolutely our intent that that we'll be able to work out deals with external providers to come in and see data in our cloud and work on data that is almost live, probably at least within minutes of being live, rather than having us pull it out of our historian and package it up in a zip file and send it through some file transfer method and all that. So our intent is to make that possible. Will there be hurdles to come across? Some of them technological, some of them related to intellectual property, whatever. I'm sure there will be, but it is our intent to bring about the vision that's on this page.
Thank you for that. And let me just add, saying that CESMII is implementing a series of smart manufacturing innovation centers across the country, focused on different areas, focused on different industries. One of them is oil and gas, energy, oil and gas. And we're talking with ExxonMobil and team, among others, to identify the best environment for that, which will be a series of real live working manufacturing assets in this industry to leverage our platform. And as I'll say a next best proxy to having live access to ExxonMobil systems, I think that would be a great approach, and in the not too distant future either. So something else to consider. But with that, we're out of time. We're at the top of the hour. Aaron, thank you for a great presentation. And I can tell based on the dialogue here, this is certainly striking a chord with our membership. And to your colleague as well, Tyler, thank you for making time to respond and for your thoughtful responses here. I hope everybody has a great day. And again, come back to our website, look for the recordings and for the slides posted there in the next couple of days. Have a good afternoon.
Thanks, everyone.
Thanks. Goodbye.